guess. All right, welcome to, I don't know what this session is called, so I'll just say to my talk and to the other talk after my talk. I'm going to talk a bit about DSLs, where we are today and where we want to go. When I say we, that's basically a team at Itemis that builds domain-specific languages with a tool called MPS. Anybody knows MPS, JetBrains MPS? Okay, not nobody, that's cool. Usually it's nobody. So just a quick look at the past. Anybody else who started at this time with modeling and stuff? Thank God that that's over, because I think this was just awful. So when we do modeling today and when we build domain-specific languages today, then these look quite different. I'm going to show you a few, so you have some idea where we are. And the starting point for these DSLs is that we want to separate the programming part, which we consider the technical aspects of software engineering, things like performance, scalability, robustness, deployment, or security. Right? We want to separate that from the business stuff, from the domain logic. We try to establish the German word Fachlichkeit in English, like kindergarten, right? Because Fachlichkeit means the domain-specific stuff. There's no real nice English word for that, I hope, or that's what we thought. Anyway, things like formulas, rules, data structures, tables, values, and of course, the tests that validate that the Fachlichkeit that the business people express using DSLs is correct. It doesn't have to, these tests don't validate that things are fast or that the program runs, that might be generated correctly, but that just the pure business logic is valid, that the tax rules, for example, are represented correctly. So we've built many DSLs in this kind of style. This one is something that looks like a Word document, and we built it specifically so that it looks like a Word document because the company originally used Word to model or program insurance contracts, and then they transformed this into a data transfer format called PDF and sent that to the other end of the world where people then manually programmed C code. You could imagine the turnaround time. And we automated that. This is the actual Word. This is the kind of DSL representation, and then we generated code from that, which obviously made the turnaround a bit faster and more reliable. Here is an example from a language that we built in the medical space, where the idea is that doctors and other healthcare professionals basically express treatments, and then the treatment algorithm runs on a phone and basically coaches a patient to take a medicine or to enter a blood pressure or something at particular points in time. And this DSL has lots of non-trivial decisions, which we represent with tables and decision trees, because if statements, nested if statements, are not understandable to doctors, but tables and trees are, something we learned. We also have, for example, numeric types with ranges, where the type system does range checking just as an additional validation of stuff they write. This is an example where you can see it's been built in Germany, where a company defines the code that underlies the software that pays out public benefits. Right? So you have to, for example, exactly define when your child was born, if you have separated parents, who has which, whatever it's called, proportion, and then, they get different support. And you can see this is a language that on the surface almost looks like a form, right? So all this bold stuff, that's kind of already there when you create an instance of whatever this thing is called, a computation. And then you can enter expressions which have primitives like dates, and they have domain-specific expressions like junger Mensch, young person, right? That's a legal term in the law, and these are represented directly in the language, so people can express efficiently whatever they have to express. This is a weird language. I guess you can guess in which other more mainstream tool our customer built the original prototype, right? And so what we did is basically, instead of using actual Excel formatting and then reverse engineering some kind of semantics, we've built a first-class notation that where you can basically mark such a boundary between two periods of time in some way, and then it formats it in black or red, but there's clear semantics associated with it. What's also interesting is that these expressions here, right, these embedded expressions, these are actually C expressions. Well, it's a bit of an extension of C, but what we generate from this is code that runs on a, the German word is Fahrtenschreiber. The English word, I know, it's a thing that runs in a truck that tracks when the driver takes breaks, right? And basically logs the legal required pause or break times. And so from these temporal rules with embedded C expressions, we generate directly the C code that runs on the actual device. So it's kind of closed loop here. Of course, we have graphical notations for system. Yes? Tachograph, exactly. Thank you. We have cases where we use graphical notations. And what you can see if you just look at this visually is a wide range of notations, right? And so that's one of the things we've learned is that in order to be able to get non-programmer business people to use languages like that, you have to build a notation or use a notation that's very close to whatever they want to use in their domain, be it diagrams with boxes and lines for systems engineering, or strange stuff, or more former style things with embedded expressions. We have other things where we've embedded math syntax into C. And this is the last example. That's a relatively sophisticated language that we've been working on recently. I think I'm allowed to say which customer. You probably, in Germany, everybody knows them. It's a company called Datev. They do the salary and tax calculation as a service for many German companies. And so there, they have to basically represent the tax law and other aspects of law in a way that's executable. Otherwise, they couldn't calculate your deductions and benefits and stuff. And so they have two challenges. One is that all the data they capture in the system changes over time. Like whether somebody is married or not is not a Boolean flag. It's a Boolean over time, right? Because the status changes. And so we have this type, TT, temporal type, where you basically define tuples of date and value, and then we have overloaded the typical operators that you have in any language to deal with these slices directly and then do the correct overlay, so that you can write code that looks like you deal with primitive values, but in fact they're all, not all, but many of them are these temporal timelines. And the other problem we have to deal with is that laws change. So from 2019, there is a different rule how to calculate whatever. And then you don't want to repeat or recode all the calculation of, for example, church tax. You only want to override parts of it, and this leads to interesting challenges in terms of types. If some of the data structures change, what is the backward compatible? How do you do subtyping, stuff like that? And so we've basically built validity dates into the language and first-class versions, and then we have interesting type checking that verifies that however you modify the data structures and the calculation rules, things are either still backward compatible or the type system forces you to override another part of the system as well to be compatible with the changing types of something else you depend on. That's trying to summarize a non-trivial DSL in 1 minute. But I'm talking about this because it's one of the more recent projects and know a bit what, I can still remember what we did. But it also demonstrates that these kinds of DSLs we use or we build for our customers, they're not like these, 5 keyword hello world kind of languages. These are really also significant projects. Anyway, so that's what we're doing now. As I said, we use MPS for that. It's a language workbench, meaning it's a tool that's optimized for building languages, open source. We've done this for about 10 years, and just to do a bunch of name dropping, there's quite a bunch of companies now that use this stuff. I always mention this because MPS has this this problem of being considered as weird and strange and niche and, you know, nobody's using it anyway, so we can't use it either. It's not quite true anymore. It's obviously still not mainstream. If you've used Xtext, another language workbench, it's used much more, but MPS has really moved outside of its niche, and it's used quite a bit. And what's nice about MPS, and the reason why we use it, is that, as I said, it has these different notations. So you can, in one program, in one file, if you will, you can mix text, diagrams, tables, trees, and also unstructured prose with embedded little fragments of structured code. That's very useful because, as I said, the notation is the surface, it's the API, it's what users see of your language. And so if you don't do that in a way that's aligned with the domain, then people don't talk to you. So just won't work. And it's sometimes funny how if you replace keywords with symbols, for example, that look more friendly than a typical Eclipse-colored keyword, can make a big difference. We're sometimes laughing about that, but that's how it is. And then for other things, a two-dimensional table is more readable than a bunch of nested if expressions, right? So some things that are objectively easier, but some are also just weird. And I emphasize this also because if you talk to most modeling people, then still today, most people would say modeling is mostly graphical, which I think is just stupid. Anyway, the other thing that MPS supports well and much better than other tools is that it supports language modularity. So you can take an existing language, embed that in another one. You can extend the language with a bunch of new keywords, different composition paradigms we've identified. Importantly, you can develop independent extensions of a base language and then mix them together, use them together without having to write, disambiguation code between these independent extensions. And that is possible because MPS uses a projectional editor. There's no parsing, so there are a few other disadvantages. For example, the programs aren't stored as text. I mean, how could you if you have all these notations, right? So you store it as XML, but still, you have a lot of flexibility in how you design your languages. And so over time, a couple of patterns have evolved. The classical, general purpose language extension pattern, where you implement a language like Java or C, and then you build extensions that are domain specific on top of that language. For example, I think I have that on my more or less next slide. Between 2011 and about 15, we've spent almost all our time building a version of, building the C99 language into MPS, and then building a whole bunch of extensions for embedded programming on top of that. Things like physical units, so you can have data types with actual physical units, and the type system does the unit conversion. State machines, obviously, half of embedded software is state machines, right? The other half is continuous differential equations, which we don't support. Some support for concurrency, and then, of course, support for components, connectors, hierarchical nesting. Lots of embedded software is structured that way. And then we've built all kinds of other things like product line variability, so you can have your basically, reified first-class if-def support, stuff like that. And we've integrated quite a bit of formal methods. That was our first kind of playing around with formal methods. We had integrated a model checker to verify state machines. We have integrated CBMC, which is a model checker for C code. So you can basically verify temporal properties not on an abstract state machine, but on the C code itself. We have played around with SAT solving, although this didn't really work too well with the complexity of C itself. We have done that in different ways later. And then all kinds of other things, to generate diagrams and stuff. This was a really major project. We spent years on this, and it didn't quite get the market success we hoped for various reasons we can discuss over beer. More recently, most of the languages we've built are really more business-oriented, meaning not so much targeting embedded programmers, but tax experts, insurance experts, people like that, doctors. And there we have noticed, surprise, surprise, most DSLs at their core have a simple functional language for doing arithmetics, for comparisons, for simple expressions, for helper functions, stuff like that. And we've built a functional language called kernel F, F for functional, kernel for core. That's why it's called kernel and not core, I guess. And most of the DSLs I've shown you before, except the C-related stuff, uses kernel F at its core. And for example, in the medical case, we have taken kernel F itself, removed about 1/3 of the expressions that the medical people didn't want, added a bunch of additional ones, for example, the decision trees, and then on top of that added a higher level language for expressing state machines for temporal behavior, like, if the patient didn't enter a blood pressure value within the last 10 minutes before the next schedule, blah, blah, blah. This is all asynchronous, and the state machine is a good abstraction for that. And again, many other different languages we've built. This is an example of integrating SMT solving into kernel F. For example, we have this alt expression, which is basically a switch, right? It has a bunch of conditions and then values it returns. So if x is bigger than or 0, then you get 1, otherwise you get 2. And of course, this is ambiguous because the case x equals 0 is kind of ambiguous. It's handled in both cases. And so we've integrated an SMT solver here that finds these things statically. And this is funny because if you talk to customers and tell them, well, we've done this cool thing where we've integrated an SMT solver with a functional language, and then, to detect things like that, they say, yeah, I mean, isn't that just another error message you output? So what's the big deal? And so the funny thing is that users don't understand the necessary work you have to do to report seemingly obvious errors, right? And of course, in this case, it's really also simple from an SMT solver integration, but there are obviously much more complex cases where you have to do all kinds of analysis in terms of data flow and types and stuff in order to figure out what the actual range of values is, so you don't report errors where there couldn't be any. This hasn't, so the way we did this here is we've built this kernel F language, and then we tried to map it to an SMT solver, and that didn't work perfectly well because the language had a bunch of features that made it unnecessarily complicated to map it to a solver. The language could have been designed differently if we had integrated it with a solver from the start, but we hadn't. And so that in the end led us to giving up on this, and I'll get back to plan B in a moment. There's another interesting project I just want to mention that Siemens colleague Daniel Raziu is working on. Anybody knows NuSMV? NuSMV? Yeah, it's a model checker, and what he does is he has implemented the NuSMV language into MPS and is now incrementally extending that language in the same way we did with C in Embedder. He does that with NuSMV, so you can build your own domain-specific ways of expressing your system, but then it's always mappable back to the NuSMV language, and it gives you the model checking and stuff like that. It's very, very interesting. For example, he has things that look like tests, but in fact, because you have these stars here, these are actually more or less symbolic executions using the model checker. It's very cool stuff. Definitely worth a watch. So, is this good enough? Is this where we want to be in the next couple of years? So a bunch of checklists here. So the notational flexibility MPS offers, that's cool. I don't need much more. You can always improve, but it works. Same for the language modularity. I guess you can make it a little bit more conceptually consistent. MPS is not an academic project. It's an industry project. It has many weird corners and many pragmatic shortcuts. But if you have some experience, this modularity works really well, right? So there's no big problem. Now, collaboration is, of course, file-based, right? So you deal with Git and branches and merging. That is not something that a business person, if people don't want to use MPS, we tell them they also have to use Git, then they have Git to hate. Works. But realistically speaking, you want more something like Google Docs style real-time collaboration, right? But with an actual language behind it. And then, of course, this stuff needs to go into the browser, right? So, because fat, bridge clients swing Java programs, business people on their PCs No. I mean, today, yeah, we can tell them you have to eat that, strange thing if you want MPS, but in the future it won't work. So somebody will have to develop something like MPS, but in the browser and with Google Docs style collaboration. If somebody has the money, let me know. I have people. Anyway, but there is another problem. Semantics definition, or, let me explain what I mean by this. So in kernel F, we have three mappings, right? We have the mapping to the interpreter. That's basically a Java program that interprets kernel F code. So we can execute kernel F programs in the IDE in real time. As the user writes code, you can run tests directly without any code generation, any overhead like that. We have a Java generator, so you can generate Java code from kernel F programs, so you can deploy them into the data center where you don't want an MPS in the interpreter. And we have this not quite working integration with a solver. Now, if you define an extension of kernel F, then the way MPS works is you can easily build a generator from that DSL down to kernel F, assuming it is semantically mappable, and then you can reuse the existing kernel F to Java generator. It also works a little bit for the SMT integration, but for the interpreter, it doesn't work. Why doesn't it work for the interpreter? Because the MPS generation infrastructure is not incremental. So you have to press Control F9, and then the whole thing starts, generates stuff, and then you can run it, right? What you really want, of course, is you want the user basically typing in their programs, and you want the tests to run immediately. No generation, no build, incrementally. And that really doesn't work. We don't have a way of incrementally, for example, translating the DSL back to kernel F and then running this existing interpreter. We don't have that until now. Of course, that's the whole point of the talk, that we're working on this. So where do we go from here? We are working on something that's called shadow models. It's an incremental, real-time model-to-model transformation engine for MPS. Basically, the idea is that if you have an input model, it's basically the surface syntax of your DSL, for example. You modify stuff there. A delta is propagated to another model, which we call the shadow model. It's, for example, a desugared version of your DSL where only basic kernel F language constructs are used. And then you can do stuff. For example, run an interpreter, right? And again, this runs incrementally where deltas are propagated down with as little computational effort as feasible. And then when you compute a result here or find some kind of error, you propagate that up along the same kind of downward chain. You go back that chain, go back up in the other direction to output that, to annotate the whatever result you've computed on the input model. And so in the context of kernel F, we're going to use this in this way, where we have the kernel F core language. It's now called kernel F2. And a bunch of utilities, and then we have DSLs up here. When you change something, you incrementally transform to the core, and then you can run the interpreter incrementally, right? Because this whole transformation is also incremental. And of course, we would also use this for code generation and for integration with an SMT solver. Now here, we have built this language from the start with the solver in mind. So we have made different trade-offs in terms of language features we've put in. And they are, we think, we haven't finished that work, but we think they're easier to integrate into, or to map to an SMT solver. We have two main execution paradigms in mind. One is already implemented, the other isn't yet. The one is basically the spreadsheet, right? So you have a bunch of code, you have a bunch of test cases, everything written in your IDE. When you change anything in the test cases or in the code which the test cases exercise, you get immediate feedback. It is exactly like a spreadsheet. You modify anything anywhere and you get an update of everything immediately. The difference, of course, we're not targeting, spreadsheet two-dimensional table syntax. We might for some parts of the language, but not for everything. But the execution model would be the same. Right. And the other typical execution is the kind of reactive, not in the sense of reactive programming, in the sense of reactive system, right? You put a stimulus into the system, it does something, typically trigger a state machine, and then output something. So that's these two kinds of DSLs we've mostly built. And again, we've implemented that mostly. So let me show you a demo. You have time for questions, by the way, if you want to ask. Why don't I see this on my screen? Okay. So what do we see here? Here we see a module expressed in kernel F that has a function here, takes the arguments and, usual trivial stuff. And here we have an assert equals, which is basically your test case. And you call these functions, and if I change something here, it directly becomes red, right? Because obviously now the test fails. So here we have this case where an interpreter is implemented as part of the language definition. And I can show you, it's annoying that I can't see this. For example, here we have an assert equals over a decision table. So a decision table is basically a two-dimensional set of nested if expressions. And this is, of course, interpreted as well. So if I change something, stuff fails. Now the interesting thing here is there is no interpreter for decision tables, right? Because they are reduced through incremental transformation to if expressions. Kernel F core only has if expressions. So if we look at the, what is this thing called? Conditional operators. Here. Then this is the code that actually runs, right? So it's basically the decision table has been reduced to nested if expressions. And so what happens here is a combination of first reducing the high-level concept decision table incrementally to this, and then on that run the incremental interpreter, which then returns or calculates a value. Let me show you something else. Here, this is another example that looks rather similar. This example has enums, but the kernel F core language doesn't have enums, it only has constants. And so what happens here is a mapping from the enums to constants. So if we look at this, it's probably here, right? Then it looks like that. We just generate 3 integer constants based on some kind of naming convention, and then we replace reference to enum literals with references to constants, and everything is still fine. Now, if I go back to the original and, for example, duplicate this, now I have an invalid program because I have 2 similarly named enum literals. Now we get an error message here that says that this is broken, blah blah blah, and this is the duplicate enum literal. But there is, of course, there is no checking rule on the sugar language that checks that enum literals are not duplicated. Instead, what happens is that when we look at the result of the transformation, we now get duplicate, top-level concepts, right? Top-level things, top-level declarations, and they must have unique names. And so what we do now is we take this error message and lift it back up to the enum declaration. So in the code that transforms down is also a little bit of code, there's a little bit of snippet that says if this thing we create has an error message, duplicate name, then lift it to this error message on the level of the enum declaration, right? And so this way we can, if you will, run an analysis on the target model and then lift it back to the source model. This is obviously the simplest case, right? But imagine we use this approach to create our SMT representation and then run the solver. We would lift the errors back in the same way. what else should I show? Maybe something about the transformation. Transformation, desugaring. This is the code, for example, that takes an alt expression, this switch-like thing, and maps it to the nested if expressions. You can see that so the problem is you have a list of things and you want to transform it to a tree of things, and that is what a fold is useful for. And so that's why we use a fold R over the cases of our alt expression and basically create if expressions for each of them. We start with a never literal. That's basically the thing that goes to the very tail, which should never occur in your code, because I mean, if you go back to this example here, then and I replace this true with another maybe is just an undefined Boolean. Now we get an error here because this table isn't guaranteed to find, to terminate. You might never select any of the 6 outputs. And the way this is implemented is simply that one of these never lits that come from the fold just remains in the output, in the final output, and then we have simply an error, a lifting rule that says if there is one of these never lits in the else part of an if, then lift this back up and say something about the table being strange, right? So it's the same idea. Yeah, the language we've built here is our own. This mapping language, where is it? Here. It's basically a functional language that internally uses lots of caching, like you would do for an incremental transformation. It's inspired by a range of published work on this, but it's not a one-to-one implementation. We're working on a paper which has the details. So, demo over. What's the status? So the transformation engine basically works. It also works for stuff beyond the hello world, although a systematic performance evaluation, we haven't done that yet. That is something we will have to do for a paper we are going to write. And there are some cases where some internal details of the transformation engine are exposed in the API, in the DSL for the transformation, where we haven't yet found the right abstractions. That is something we need to fix, because normal people don't understand why you have to define a fork in some places and not in others. If you understand how name resolution is done and how identities are managed, then you understand, but most people don't, and they shouldn't. So in the context of kernel F2, we have basically implemented the core language. We have the basic set of extensions. We have an interpreter that is mostly done. The generator is not yet done, but that's just work. We've built dozens of those, and we have not yet seriously worked. Well, we've done a lot of work on SMT integration, but not of this language. So there's also some research we need to do, because it's not that useful if you can do the transformation incrementally, but then the solver isn't incremental, right? So then, if that restarts everything every time and takes 5 seconds, then that's not the best situation. So there are some patterns of how you can use non-incremental solvers incrementally by cheating a little bit in terms of how you send the data and do stuff, but that's something that needs a bit more work. All right, questions? I'm done with the talk.
Hello, you briefly said that modeling is also graphical. This statement doesn't make sense in your opinion, so I would be interested why. And also maybe you can say why generating from a model is inferior to your approach, or where it really shines, especially from a practical standpoint.
So I hope I didn't say that graphical modeling makes no sense. What I said was that thinking about modeling exclusively as graphical notations makes no sense, right? Because sometimes you want tables, sometimes you want text, you want expressions. I mean, there are people who say that if you have expressions like 4 plus x greater than y, that you should model that in your graphical modeling tool as graphical boxes with things. This makes no sense. So you want to be able to mix notations. This is, for me, totally obvious. And the reason why languages like UML are basically, well, you can say it's only graphical. Other people say it's basically a textual language wrapped in boxes, right? I mean, the function signature is textual, so it's already a mix. But so, yeah, I don't understand why. So I think the reason why people look at modeling mostly as graphical things is a historical tool issue. Historically, programming tools were text and modeling tools were different, so they had to be graphical. And so that's what's still stuck in many people's minds. But you want the notation to be whatever it needs for your domain. Doesn't matter. What counts is the abstractions, not the notation, to make it a model as opposed to code. Although that's another discussion, what's the difference between model code. We won't do this now here. What was the second question?
Why designing a DSL and having the user actually write or implement programs in the DSL is superior to designing some UML diagram and then using this? So from a practical standpoint, I mean, I just have never experienced a user implementing something in a DSL herself. So it would just be interesting to hear your anecdotes on how users take this, or why this approach makes more sense.
Well, because the language that we, for example, built for these text people is built in a way where the central challenges of their domain, temporal data, versioning, stuff like that, is directly available as language constructs with IDE support, with code completion, with type checking in a meaningful way, with meaningful error messages, with an IDE that knows about all this stuff. If you did that in Java, if you programmed it in Java, you can't do much about syntax, you can't do much about error messages. If you try to do it with UML, you better shoot yourself, because you can't express text calculations as a bunch of rectangles and class diagrams and sequence diagrams. It just doesn't work. So the only way you can do this, if you want to do better than just here's an API in Java, is to build a DSL. In my opinion, I might be biased. But more questions?
Hi, have you considered Racket for your projects as well? Like,
no.
No? Like,
no.
Do you know, like, do you have, you didn't take it into consideration at all?
No, I mean, we've done MPS for 10 years. It works well. It has this notational flexibility that Racket doesn't have directly or obviously, right? But I think Racket is probably the closest alternative to what MPS does, although it does it quite differently. But it does have language extensibility. I've seen examples where they've used non-textual notations, although that looked a little bit non-first class. I don't know. So, yeah. But I can't give you a detailed, comparison to Racket.
Thanks for the talk. A slightly broader question. Is this approach of putting DSLs directly into subject matter experts' hands something that you think is underused within industry?
Only used where?
Should it be used more?
Of course.
Yeah. Like, I guess the real question was, what do you think it is as the barrier that stops us from employing this technique if it is as compelling as you've described?
Yeah. So there's all kinds of barriers. People think it's crazy to build your own language. They think it's too much work. They think learning a new language is more complicated than learning an API, which is bullshit, because the IDE can give you much better support than for an API. So there's all kinds of, if you will, prejudices, right? And it becomes worse the higher up with management you talk. What? We're a tax company. We're not going to build our own languages. Now, that particular tax company has done that for 20 years, so it wasn't a problem there. But realistically, the arguments against it is that you tie yourself to a particular tool, right? So if you build a language in MPS, you can't port that language definition to anything else. The code you can. You can always export it as an AST and import it somewhere else if you build the language there again. But you tie yourself to a tool. That is, in my opinion, well, that and the fact that finding people who can build DSLs, it's not that easy. There are not that many. It's a niche, like in the grand scheme of things. So these are the two arguments against it that I would say are valid arguments. Most of the others are prejudice. We have lots of examples where we've also published a bit about this, where it clearly shows that, for example, at Datev, right? We built a prototype within a few weeks that handled this temporal data problem and the versioning. They worked on a Java-based prototype for months, and the only thing they did was adding 2 numbers in a web service stack. So admittedly, the prototype was about infrastructure, but they had no idea how to tackle the core complexities of the domain. We did it within a few weeks, which is what then triggered them to go this route. So I don't know why I said this. Yeah. More questions? Yeah.
You had a slide that seemed to allude to iterated domain-specific languages. Do you come across this in industry, that you have a DSL and then it evolves to contain another DSL? Well, I would say what often happens is that you start with a DSL for one subset of the overall space that the company works in, and then over time you find, oh, well, we could also do this with a DSL, and then you build another one, and then the question is, how do those fit together, assuming there is some overlap? And well, that's just basically language design, and by using a common foundation, like for example kernel F, you at least make sure that expressions are the same, so and maybe the types, and so the language have already a kind of common feel, and then it's not that much of a problem to align those. So the thing that one DSL at some point has to embed another one is rather rare. It's more like you have a language with embedded expressions, and then you have 5 other languages in that company that also need to do that and somehow interact with this first one. That happens regularly. It's also something we encourage, right? We want people to think in terms of ecosystems of related languages.
Can you describe a bit how introducing the subject matter experts to writing DSLs actually happens in practice? Like, what are the issues you run into? How do you actually do it? Like, you sit them in front of MPS, what's next?
Yeah, I mean, they sit in front of MPS, which is, if you will, it's a bug and not a feature, right? You want to have them sit in front of a browser with a much simpler UI. Often we get feedback that, well, the language is fine, but why do we need 5 million buttons and 7 million menu entries around it? These can be stripped down as well, but still, it's an IDE, which some people don't like. But yeah, you typically start with pair programming. You involve the domain experts in language design to get feedback early, depending, of course, a bit on their willingness to entertain this idea. And you always have a subset of people who just decide that I'm not a programmer, I'm not going to do this, and just get rid of these people somehow. No, I mean, the point is, whatever you do, if you want to do something new, you have 10% of people who hate it, and you can't do much, right? You have 10% who are eager, 70% who will kind of jump on the train when it kind of works, and you have 10-15% who hate it, and you just want to make sure you're not discouraged by them. And the rest is really dependent on the particular projects. What really makes a big difference is building a language that faithfully represents the domain they know, probably after some clearing up and some kind of reverse understanding of what their domain is actually about, because most people can't explain that to you, right? Yeah.
Thank you once again, Markus.